right. Good morning. Can you all hear properly? Good. Thank you, Diego. All right. So today is the last day. Thank you for geometric short course. So it was only 3 times 4 hours, but I think we did quite some work, and yeah, you can be really. And today it's going to be a bit more relaxed, so a lot less writing and a lot more conceptual discussions. So we can rest a bit. I'm going to organize the discussion, and I know that some of you asked me to cover specifics such as fluid structure interaction. So what I'm going to do is, and that I couldn't cover it, there are 2 options. The first is I put you in touch with people in the field that actually can for fluid structure. Any other topic that you may be interested in relation to IGA or not, by the way, do not hesitate to ask me if you think I may have an idea who to, if you're stuck somewhere, which happens from time to time. So today I'll be going through a few examples, and I'll be all with other ideas to handle interfaces and geometries that is complicated and evolving over time. So you're from that, if I will go back to the slide which explains you remember that we talked about 2 approaches essentially to where we decoupled the geometry from the mesh, and that is what you see the method, mesh-free methods to some extent. And we talked about IGA a lot, and IGA is quite the opposite approach, where the mesh is actually linked to the geometry, because the mesh, or let's say to be more precise, is completely connected to the geometry, because the same basis functions are used in order to represent both geometry and unknown field variables. As you see, you could consider the problem quite differently, where you would say, I do not want to know about the geometry when I am to be approximated on some space, but I do not necessarily want the geometry to be approximated on the same space. For example, you might want to say that when you have a PhD thesis on self-healing concrete. So in that PhD thesis, the student was working on the propagation of cracks, and the breaking capsules, which are made up of a shell, which is a relatively rigid material containing a healing agent, and try to glue the cracks back together. So I suppose this is applicable to problems. Is there a problem? So I hear that some of you have breaks in the audios, and apparently it's not coming from you because me. All right. Do you still get problems with the audio now?
Yes.
Yes. All right, this is not good.
There was a major problem yesterday in whole world, so it's possible it's because of that.
Because I can hear you very well. What I'll do is I'll get rid of the video in case maybe completely useless. So, okay, video off. Does that change anything? I also got rid of most of the applications on the computer in case it. All right. Okay, I'll try again. Hopefully that works. Checking if I'm connected to the proper. Okay, so is that better or worse now? It's the same. Okay. Okay, I'll try minutes. If in let's say 5 minutes there is no difference, I'll move somewhere else and try from there. So I will need then 20 minutes, and then if that works, it works. If it doesn't work, then we'll figure out something different. All right. So let's go. All right, as I was saying, we have two ways, geometries that are complex, and one is to couple the geometry with the approximation, as we do in IGA, and the other is the opposite. So now I'm going to show you how it's possible to do quite the opposite. I will contrast the two approaches so that you can have an idea when you choose a method, how to actually choose it. All right, so these slides I showed you last time. So we talked about composites, delamination, and so on. Okay, and now instead of coupling CAD and analysis, we're going to think about how we could decouple the two and see how. Those are papers and references that are going to help you figure out what are the published in the field. So there are quite a number of names around that idea of decoupling. You will hear words such as fictitious domains, embedded boundary methods, virtual boundary methods, and Cartesian grids. So we like to separate the field variables and the boundary discretizations. So more recent methods include extended finite element methods and cut finite element methods as well. The point is that
so the paradigm is like this. You would like to immerse. This is why one of the original methods was called, and you'd like to immerse the boundary inside the mesh. So the mesh is what it is, and the boundary is what it is, and they do not have to conform. So that can be helpful when you have, as in the bottom figure, you have interfaces such as aggregates, for example. So these aggregates can be numerous, and meshing them, as you saw on the first slides that I showed at the beginning of the course from Jean-François Remac, if you remember GMesh, the idea there was that he was trying to mesh thin and long compared to the average, let's say, characteristic length of the cube. And he had millions of elements, I think 100 million or so. And well, you could see that this is the state of the art in the field, right? And let's say the density of these rods could have been higher. So sometimes you have a more dilute mixture, a slightly denser mixture, in which case generating the mesh is even harder, because the rods can get arbitrarily close to each other, which means that two rods which are quite close could become very small. And on top of that, they have to be constrained to stick to the boundary of the rods, which is an extra constraint. And if the elements are small, that can lead to the mesh generator failing. So the idea of immersed boundaries for these complex, let's say, geometries or microstructures, and in many other fields in biomechanics, for example, the idea is that you would like the interfaces to be independent from the mesh, such that you can simply inclusions and whichever other interfaces you may be interested in, such as cracks or healing agent interfaces and so on, such that right? So that's the idea. And you can do that for interfaces like geometrical interfaces and material interfaces, but also even for the geometry itself. So if you have these two rings that are interlaced, these two things are modeled without having a conforming mesh at all. So the mesh is arbitrary, let's say, with, and is embedded in the mesh, right? And only the elements which happen to be inside the volume are going to be activated, and the elements which are outside the volume will be destroyed, let's say, in the assembly process. So now let's see how this can actually be done practically. One of the early papers said Bilichko, it was called a structured XFEM. Some later papers are by Éric Béchet and Nicolas Moès, and other colleagues from École Centrale de Nantes. And later, we published a paper in CMAME with Moumnassi in 2011, already 10 years ago. Still breaking. Is it audible or is it really unbearable?
Okay.
Okay.
Can you hear me
Can you hear
now?
me now?
Can you hear me now?
You're echoing.
You're echoing. Yes.
Yes.
Yes. Okay, it should be better now. Is the echo still there?
No,
No. Can you hear me unbroken?
I do.
Okay. So I think I found the problem. I really need to fix this then. Okay, it's just going to take normally 1 second. Sorry about that. Okay, can you see the slide again?
Yes.
Okay, good. Finally. All right, so I think that problem is solved now. All right, so the basic idea is like that. We would like to embed the geometry inside a mesh, and the mesh is supposed to remain fixed, right? So for example, here we have a, you see we have an interface, and that interface is not conformally meshed. So, for example, here you see this element. I hope you see what I'm drawing. The element is actually split. So if you look at the element there, the element is split, and the interface does not know that the element is where the elements are. And the idea is that the elements that are inside will be activated. So if an element is fully inside, like this element, it will be fully activated. Some elements, and that one as well, almost fully inside. Some elements will be split, like for example, that element is split. And we will have different cases, but what we do is we will have integration points inside through a triangulation, integration points outside through a triangulation. And well, the idea is that the integration points inside will be associated, let's say, with this Young's modulus E1, and the integration points outside, let's say those, will be associated with Young's modulus E2, which means that you will have the ability of having 2 Young's moduli inside the domain. But that's not sufficient, as we said last time, because if we do only that, we will have a smeared interface, which means that if we plotted the displacement and the interface was here, if we plot the displacement and we do not use any enrichment, but instead we simply use an average modulus, then inside the element, we would have a linear curve, and the linear curve would have a slope, which is some weighted average of E1 and E2. But the slope will be constant, which is incorrect, because if this is the displacement field and this is the distance, and for example, we plot along this direction, x, then that is what you would see. You would see no kink. And the reality is that you should have a kink. So you should have, let us say, a slow increase first, because let us imagine that E1 is less than E2, and then a faster rise. Okay, so this is slope E1, and this is slope E2. So here you need a kink. And we said in IGA that there are ways to have kinks, directly embedded inside the elements by multiplying the knots. So using knot insertion locally, increasing the multiplicity of the knot, that allows you to have these beautiful jumps in the derivative and maybe in the function itself. Okay, so that's the idea of this sort of embedded approach. Now, how does it work? Well, you start from a mesh, which the mesh is completely arbitrary in that case. I mean, this is not the general way of doing this, because if the mesh is fully arbitrary, usually things will not work very well, because locally, as I was mentioning at the beginning of the course on the first day concerning this astrocyte problem, which Sofia Farina in my group is working on, you have such small areas, small volumes in the dendrites that you will have a problem in trying to picture it. So, for example, if you have an octagon
chaise. Tiens me voler ta chaise avec tes besoins qui dort aussi. J'attends avec impatience ce truc. Je pense qu'il y a une erreur de chaise à couloir. Oh. Je sais pas, Romain il t'a blâmé direct alors. Tu as joué à Sophie? C'est pas la mienne. Elle est venue cette semaine ou pas?
error look like? Okay, so you can create.
Donc, pour la dernière fois, il y a aussi le mécanisme qui a construit.
C'était une affaire de. Sachant qu'on a le test super
Error. Is the best possible solution to the problem. Okay, so that is super important because by doing that, you can actually understand that you cannot do anything better than the finite element solution in the sense of this norm associated with the bilinear form A. Okay, so maybe that was a little bit too abstract, but I think it's nice because it gives you some sort of geometrical representation of the error. Yeah, who is speaking? Hello? Okay, oh, that's fine. All right, so all right, so now what we want is we want to compute, and you will see why I'm doing this. I'm doing it very fast without any of the rigorous statements that would be needed to do that properly, but I give you the sort of feeling for the a priori error estimate so that then you can understand why we do what we do. You will see. I think it's quite neat. So now you look at, you want to find an approximation for this. You want to find an approximation for the error of the operator, of the finite element solution. Okay, so how do you do that? What you do is you can measure the error by computing some norm of the error. And here there is really
in almost an infinite number of ways you can compute this norm. So you can choose any norm, really. So let's just not worry too much about what the norm is. Let us just say that it is a norm that measures the distance between u and uh. So for example, it could be the L2 norm. So the L2 norm, if we select L2 norm, this is the norm, so the norm of a vector, let's call it x, if it is the L2 norm of x, and x has 3 components. The L2 norm is x1 squared plus x2 squared plus x3 squared, and the whole thing square root, right? So that is the idea of the L2 norm. So it measures the sum of the squares of the components and takes the square root. So this is a possibility. You can compute, for example, the L2 norm. Okay, we usually write it 2. And we cannot write exactly what it is equal to, but we can say that it's less than something, and that something includes a constant c, which is some constant which does not depend on the mesh. So it means that constant is a constant with respect to h times h. So h, remember, is the typical size of an element, so that guy. And then to some power, right? So remember again that when you refine the mesh, okay, let's go back. If you refine the mesh, let's take this and bring it downward. Let's bring that here. And okay, so when you refine the mesh, what's going to happen is that this h will go smaller and smaller. So if you take this guy and you refine, so you will get a smaller a, you will get a smaller h, for example, by splitting this element into sub-elements, like using edge bisection, as I'm doing here by hand, which is quite nice. So you can use edge bisection, and you see that h now is going to be smaller and smaller. Now it's probably h is the area of this thing here. So h goes to 0. So h typically is going to be much less than 1. All right, so that means that if you compute this thing that I've written here, if you compute that, what's going to happen is that you would like this coefficient, you'd like the power to be as high as possible, because if the power is high and h is small, then that thing on the right will go to 0 very fast, okay? Because this guy is much less than 1. So you would like this exponent to be as big as possible. Because if the exponent is very big, and if h is very small, you will then take a very small number to some very high power, which means that you will get an even smaller number. That's the idea. So if, for example, h is 10 to the minus 2, and the exponent is 2, then you get 10 minus 4 as an error, which is much better than if the exponent was 1, in which case you would get 10 to the minus 2 as an error. So the idea is that you would like this exponent to be as big as possible. So, and let's see what Sea's lemma is actually saying, which is one of the lemmas that leads to the a priori error estimates for finite elements. It tells you that this exponent is the minimum of 2 numbers. The first number is the polynomial order. Plus 1. And now will come something that is at the beginning a bit difficult to understand. So here we say m equals 2. This is the L2 norm. Okay. This is the norm in which you measure the error. But you will see that it doesn't really matter, because you will see. R, this is the regularity of exact solution U. So that means how many times you can safely differentiate U without getting some horrible results. So for example, if U is discontinuous, R will be very small. I'm not giving you numbers because it doesn't matter at the moment. We're not here to what is important to know is that if U is smooth, that implies R is large. And if U is so-called rough, this is what people call a rough solution, is something which is not smooth, not regular. So smooth is also sometimes called regular, and rough is irregular. You know, so rough is something discontinuous, more or less, close to discontinuous, or varying very fast, or singular. It could be also a singular function. And then R is small. Okay, so if you have a singular function, if you have a discontinuity, if you have a discontinuous derivative, or if you have any weird thing, U is rough. Okay, so a typical smooth function is sine. You know, that's a very smooth function. A typical rough function would be something like an exponential varying very fast close to a wall, for example. That would be rough. Another rough function would be something with a jump. That would be rough. Something with a kink. That would also be rough. And you can imagine arbitrarily rough functions. I mean, of course, the Cantor set function would be the worst possible one, probably. So you have that guy, and you're trying to figure out what is this exponent, right? Because this exponent here is the most important thing. You know, you want this. This is what you cannot control, because you can't control h. You know, you can refine, and refine. So that's very nice, but you cannot control. You can also control p, because p is the polynomial order. So you can choose to increase the polynomial order. You can also control the norm in which you measure stuff. So you can say, okay, I want the L2 norm, so m is equal to 2, for example, if I have the L2 norm. But you know, it could be that you want to measure it with some other norm, like the H1 norm, or maybe you want the H5 norm, or whatever. That you can also control. But what you cannot control is something which is really annoying, and that is the roughness of the solution. So this R here, that you cannot control. So if R is small, it means the solution is rough. So that is equivalent to having a rough solution. So if R is small, then the minimum of R minus whatever and P plus 1 minus whatever is probably going to be governed by R. Okay, so what does that mean? So it means, essentially, it's very simple. So you have, let's write again this power. You have h to the power min of, let's just say, polynomial order plus 1, comma R. Let's forget the m for now. So now what happens? If R is small, what good does it do to increase P? So, you know, because typically, you know, if your solution doesn't work out, you know, let's say you solve a problem, it could be an L-shaped problem, for example, you know, that sort of problem, and you apply some boundary conditions on that, whatever they are, so maybe like this, for example, or like, you know, you apply some conditions on this, and then you will get some streamlines, and, you know, so the solution will be looking the way it looks, and then, you know, you will have here some large gradients at the corner. And the same thing if you look at the crack problem, which is the limit case of this, when the angle is actually 0. Okay, so now if you pull on this, you will have, you know, streamlines which will go like this, will have to go around, and so they will be all compressed around the crack, and so you will have high gradients around here. So you have, in fact, a singular solution usually at the crack tip. All right, so that then what will you do? So let's say that you have a certain h, which in your opinion is very small. So that's, you know, that's fine. You cannot get it smaller. maybe what you would think is, why not increase P? Now that would be a logical thing to do, right? Because you say, okay, if I put more information in the solution, why shouldn't it work? But as you can see here, it's completely useless to increase P, because increasing P just makes that thing bigger. So that thing will increase. But if this guy is small, we have a minimum, not a maximum. So you can increase P how much you like. The error will not decrease. No? It will actually, the bound of the error will not decrease. And this is why if you solve a finite element problem with a solution which is discontinuous, you see that phenomenon, which is called the Gibbs phenomenon. So if you use a low P, you will get something like, maybe something like this. So let's say this is P, I don't know, equals 2, just to say something. Then if you increase P, you will get stuff like this. Say P equals 3. If you keep increasing P, what you will get is something like that. And if you keep increasing P even more, then you will get something like this. So P large. So it means that if you want to capture a solution which is, U discontinuous, and that also happens with singularities, by the way, and if you increase P, well, then the solution not only doesn't get better, but it gets worse. So that's why if that happens, you cannot increase P on its own. You need to increase P in a smart way as you refine H, but H cannot be refined uniformly. It has to be refined in a smart way, which knows about the structure of the exact solution U. And that you can do. There is very nice work by Mark Ainsworth, who is probably the world of authority on these methods, and Oden and Prudhomme. So those are clearly, and of course, Ivo Babushka. So if you want details about that, you can take a look at their work, because they are clearly the world-leading people in that area, and the first people that did work on that, I guess, from my understanding at least. So that means now we have a bound. So that's cool, because we have now a bound for E. So this, we know that the norm of E, whatever norm, let's forget the norm for now, is less than C times H to some power. And that power is governed by R. And R is the regularity of the solution. So you see, we are in quite some trouble, because whatever we do about P, we cannot decrease the error. So all we can do is decrease H. There is no point in increasing P. And that is going to be exactly why people like Ivo Babushka started the idea of partition of unity enrichment. In his 1995 paper, he says that the error is only as bad as the worst approximate. I think the sentence is exactly that one. And what does that actually mean? So it means that if you cannot approximate the solution that you try to approximate, so if your solution space is super rich, like a very high order P, that guy, but your solution is unfortunately discontinuous, like the one we drew, right? Like this. So you have a discontinuous solution, but you're trying to find it, you're trying to approximate it with functions that are not appropriate. Then you can do whatever you like, the error will not be decreased efficiently. And so this is the whole idea behind the partition of unity method. And this is exactly why, so this is now what I would like to show on that, which I hope you still see. If not, then we'll do something about it. Okay. All right. This is actually working very nice.
Let's touch wood. Okay, so discontinuities, large gradients, singularities, boundary layers, oscillatory behavior, all these things are difficult to tackle. Okay, so vibrations, impact, actually acoustics is another one. Boundary layers that you see in in fluid flow. If you have an obstacle in flow, then you will have these boundary layers around, and you need to figure out what happens here close to the wall. Singularities, that is what happens if you have a crack like this, for example, then here you will have a singularity. Yield lines, shock waves, so you name it. There are huge numbers of cases where the finite element out of the box is not the best solution method. However, the nice thing about finite elements is that you still have this C H to some power min of P plus 1 R. So you still have H, right? And so this H can, and if H goes to 0, what happens is still that you can do something, but that then comes back to the question, can you mesh properly and in an efficient way and in an accurate way? That's the question. So that's why everybody is so concerned about meshing and trying to come up with mesh-free methods and so on, because that's really a key central issue. Okay, so what else can we do? So let's say that we try to refine as much as we want, but we actually want to get rid of this mesh because it is difficult, it's messy. So we say, okay, we want something a little bit more elegant. So what can we do? And this is the idea of enrichment based on partition of unity. The idea is, again, to make the mesh independent of any phenomena that we want to look at. And then we want to improve the convergence rate. What is the convergence rate? The convergence rate is the exponent. So when you have this CH to some power, alpha is the convergence rate. All right, so convergence rates, that means alpha. It means if you decrease H, at which speed does the error decrease? And of course, you would like the rate of decrease of the error to be as large as possible, because if you decrease H by 10, you'd like the error to be decreased by 100, for example. That would be quadratic convergence. If you decrease H by 10 and the error is decreased by 1000, that's cubic convergence. And that's super nice because you only use 10 times more elements, but the error is decreased by a factor of 1000. And in your everyday calculations, you will see that. So for instance, if you try to solve a problem, which you see sometimes in biomechanics, in certain conferences, you see people using point loads, and under the point load, you will have a logarithmic solution. It's basically log R. So the log of R being the distance to the point load. So the exact solution looks like something like log R. So log R is naturally infinite when R goes to 0. So if you try to model that using finite elements, you will have a case where this R is very low. What did I do? You will have a case where this R is very low because the R is the regularity of the solution, right? So if R is low, then your error level will simply be converging very slowly. Okay, so that's the idea. Okay, so again, discontinuities are what? Well, they can be strong discontinuities. So you see here we have a jump in the solution, but they can be also weak discontinuities where you have a kink in the solution. So here the solution is U is discontinuous, and here grad U is discontinuous. Okay, easy. Now, how can we enrich the solution? What is the idea behind it? So the idea, in fact, came around so global enrichment, that's what we cover in our book with Sundar, in the 1970s by Strang and Fix. So in their book, I think it's 1972, or about that time. So Gilbert Strang is a professor at MIT, and he still teaches, and he has OpenCourseware material, which I really highly recommend, on MIT OpenCourseware, where finite elements is taught by him in a super intuitive way, and I think you will really enjoy that if you take the time to listen to it. I did, and I really learned a lot. So you have two approaches. So they talk in Strike and Fix about global enrichment. And so the idea is that you look for a solution UH as a polynomial which is localized. So we write it exactly as before, Ni ui plus enrichment. But this enrichment function is global. So it will be, for example, a global enrichment function g of x, which means that UH of x is a partition of unity as usual. So this is what we saw in IGA. This is what we see in Lagrange polynomials. This is what we see everywhere in mesh-free methods as well, with MLS shape functions instead of Ni, but it is as usual, you know, these functions which are either overlapping or not overlapping and so on. If it's in IGA, we see this, you know, these beautiful curves like this and so on. We see these overlapping B-splines. So these functions here, the NIs, can be any partition of unity. You can use also, like in mesh-free methods, these overlapping kernels. So that is a very, very standard part. And on top of that, you add a function, g of x, and this g of x is nothing else but a global enrichment that knows about what the solution looks like. So the smart thing about that is that you say, okay, I know that my solution is not polynomial because maybe it has some singularity. Let's imagine that we go back to this point load and we know we have a log R singularity. So we have this log R singularity. We don't like it. So what we say is, okay, well, I'm simply going to add log of R to the problem, right? And this is going to be a global enrichment function, and this global enrichment function will live on the whole domain. And so that works. It's not a problem, but you can immediately imagine what the solution, what the matrix will look like. You know? So if you have, let's make this part that color, and let's make the other part this color. So we will have a big matrix. We will have a standard path, which is this, and it will be basically a block diagonal matrix. It will be sparse. And then on top of that, we are going to end up with two blocks. And these two blocks will be, let's say, separate from the rest. And it will be associated with some degree of freedom we can call alpha, for example. And here will be the row associated with alpha. Here will be the column associated with alpha. And as you can see, although here you have a very sparse matrix, the presence of these extra blocks will get rid of the sparsity of the matrix. So that's one disadvantage. And the other disadvantage is that you cannot localize the enrichment. The enrichment, and this is related, it has to exist everywhere on the domain. Okay, and that's not so nice, because let's say that you don't have one point load, but you have a number of point loads, and you would like to enrich with, you know, different functions for each point load. Then the problem will be that all point loads will coexist over the whole domain, and they will pollute each other, and that is not what you want. So that method is very useful for certain cases. In particular, if you have oscillatory behaviors like Helmholtz problem, you can globally enrich and add plane wave solutions to your Helmholtz equation, to your Helmholtz solution, for example. And our PhD student Chintan Jansari in our group, in collaboration with Elena Toshenko, is just submitting a paper on how to do that with IGA as a basis underlying shape function, set of shape functions Ni. And, you know, this really works. But if you need to have a local enrichment, and if you would like to maintain the sparsity of the matrix and the flexibility of the approach, then this global enrichment approach is perhaps not the best. And this is why Ivo Babushka came up with the idea of partition of unity finite elements, partition of unity methods, PUFEM. Okay, And now there are quite a number of ways that you can think about this extrinsic enrichment and intrinsic enrichment. So in fact, there are really many different methods which came out of the original UFEM, which is Babushka and Melenc. So there are several papers, 94, 5, 6, and later. After that, Nicolas Moes and Ted Belichko and Black, 1999, came up with the extended finite element method, and then Moes, Dolbo, and Belichko, a famous paper in 1999. In parallel, Stroboulis devised a method which is called the generalized finite element method. The major difference between the two is that in generalized finite element methods, you use pre-computed, numerically computed enrichment. I will explain that to you in a minute. And then enriched element-free Galerkin methods, which are essentially by my friend Giulio Ventura in Italy, at the time at Northwestern as well. And this idea is that you would like to take mesh-free shape functions and enrich them with local knowledge about the solution. And then finally, HP clouds, which are by Duarte and Oden in 96. Okay, so those are different methods, different papers you can look at if you're interested in them. Let me know if you don't find them. I can give them to you and also give you a PDF of our book so that you can take a look. And the intrinsic enrichment looks like completely different, but I'm not going to talk about it because it's let's say it's a niche approach and it's not used these days anymore. We did say, okay, elements with embedded discontinuities are used, but the other intrinsic the partition of unity, enriched weight functions, and enriched moving least squares, I think, are relatively niche methods. If you're interested in enriched weight functions, you can also look at the work of Barbieri. So it's Ettore Barbieri. He's now in close to Tokyo, working in the research center there, and he's one of the first players who worked on that. So the basic idea of intrinsic versus extrinsic is that for intrinsic enrichment, you do not need extra degrees of freedom. You simply modify the shape functions such that they look like what you wish them to look like, meaning look like the exact solution to the problem. That's the idea. So you modify the shape functions, but you don't modify the approximation globally, meaning that you do not add any other function to the space. You just modify the existing space. All right. So this is something which is a detail at this stage. Okay, now we're going to take an example, which is a perfect example of how enrichment works and how it can help model, for example, fracture. And if you guys are interested in Limerick, for example, or elsewhere, we could do an extra course only on XFEM, and that would be a completely different course. This is isoparametric finite elements. So this is a 1974 paper by Barsoum. This is the Barsoum element. And the idea of Barsoum elements is that you take a P2 element, which is polynomial of order 2, as we talked before, and you move one of the nodes 1/4 from the summit of, so from the edge, from the vertices, from the vertex of the element. And then what that does is that it creates a singularity of 1/√r. So I couldn't believe it the first time I read this, but if you do the calculations, you actually see that moving that node at a quarter distance creates this singularity in the strain inside the element. So that is quite a very simple way to address the problem that you have, because you create a singularity, and this singularity is exactly the singularity you want at the crack tip. So this is a result of linear elastic fracture mechanics. You automatically see that by solving the equations in linear elasticity, you will get a singularity of type 1/√R for the strain and the stress. So what you can do is move that node, and you will automatically get back the singularity. Sorry. Okay, so now let us ask ourselves what it means to use partition of unity. So until now, we talked about the fact that NURBS basis functions are partitions of unity, but they are not the only ones. For example, Lagrange shape functions that you see here on this picture, those are also partitions of unity. And we said when we were looking at B-splines that if you simply add n1 and n2, for example, it works also here. So if you take any point, let's say here, you take the value here, and you take the value from here to there, okay? And you see that this value is the complement to that. So these two things are summing to 1, right? So n1 plus n2 is equal to 1. So that means that everywhere on the domain, you have a sum of functions which is 1. That can be proved if you have a partition of unity as in terms of your basis functions. So until now, we wrote this sum over I from 1 to n of capital N sub I of x. If that guy is equal to 1, then you can reproduce any constant field. So it means that you can reproduce a constant. And that is called consistence or consistency. And this is one of the conditions for convergence of the finite element problem method or any other numerical method for that matter. If you remember what we said about B-splines, we said they are positive. We said that they satisfy a partition of unity as well. Okay, so that is what we meant about this. And this is how it works. So if you want to reproduce a function, okay, so let's, if you go back to the previous thing, you see that you have the sum of the functions, but you can imagine that there is a hidden 1 here. Okay, and this is equal to 1, right? So you can just multiply by 1 and it doesn't change anything. So here, this 1 is replaced by p. It basically means that you multiply the partition of unity by p, and you can reproduce p. So what does it mean to reproduce p? It means that
to do that,
if p is in the basis, then you will be able to exactly reproduce p. So it means it's extremely powerful, because it means that if you put log r in the basis, or root r in the basis, or sine theta in the basis, or whatever other function you may want to put, exponential of minus alpha x, for example, with alpha a big number or a small one, then you'll get something which can be reproduced exactly. And that is the idea of partition of unity. So now if you look at the term in the approximation would look exactly like this. So it's a sum of partition of unity functions that could be B-splines, that could be Lagrange shape functions, they can be NURBS, they can be moving least squares, radial basis functions, they can be spectral functions, it can be anything you like, as long as they form a partition of unity. And then you multiply this by the function you're interested in, and you have to put some coefficients. All right, these are the adjustment coefficients which you're going to solve for. These are the unknowns. And these unknowns, they are useful such that you do not end up with the same case as the global enrichment, where you had ux equals the partition of unity plus g of x times a. Well, actually, I used a different number. I think I used alpha.
We're going to cover how to use OB
times alpha. And this alpha, there was a unique alpha, only one. Okay, so for the global enrichment, The global enrichment uses alpha, which is a unique alpha. So you can only scale the function globally. You cannot scale it locally. But here, instead, this Qi is going to allow you to scale the contribution of the enrichment functions locally in each element. Okay, so we're going to see now what that means, because it is really cool. So let's look at an example. That will be a perfect illustration of what we talked about yesterday, actually. Okay, so we are going to start with that problem. That problem is a Laplace problem. So in multiple dimension, it will be Laplacian. It's in fact a Poisson problem plus f equals 0 plus boundary conditions. This is typical of an elliptic problem, diffusion problem, as we talked about before. And it's defined on a domain which goes from 0 to L. And at 0, we have no displacement. At L, we have U equals UL, which is imposed. So you imagine that you take a bar and you impose a displacement at the end of the bar. And if you use integration by parts, so you can easily see that you multiply this by a weight function W. So if I write this U double prime, and I want to derive this weak form, what is going to happen is I have U double prime plus F equals 0. I multiply that by W, so I get U double prime W plus F W equals 0. Then I integrate over the domain. I get integral of U double prime W plus integral of FW equals 0. Then I can use integration by parts, which tells me that this is U prime W prime minus integral of U prime W prime plus integral of FW. All I did is I used the product rule. And this guy here is nothing else but the evaluation of U prime W on the boundary. And this will lead to two terms. One term will be associated with the Neumann condition, which will be associated with this U prime, the derivative, so the flux. And the other term will be 0 because W is 0 on the Dirichlet boundary by definition of the test space. So at the end of the day, you end up with minus integral of U prime W prime plus integral of FW equals 0. So that's the weak form. Okay, and this is exactly what we have here. All right, so this is the linear form that we have there, and this is the bilinear form which we have here. Okay. So that's the way you derive the weak form. So I skipped one step here, which maybe you'd like to understand better. This is the integral of U prime W prime. So if we go here, integral of U prime W prime the omega. This is the evaluation of U prime W over gamma, but gamma is the union of gamma Neumann union gamma Dirichlet. On gamma Dirichlet, W equals 0 on gamma Dirichlet, which means that this thing boils down to U prime W on gamma Neumann, because the other part must be 0 because W is 0. And on gamma Neumann, it happens that U prime equals Q imposed, which is the Neumann boundary condition, which means that this thing is simply Q omega over the Neumann boundary. So if you write this in finite element terms, you would get essentially integral of grad U dot n times omega on or W on the interface. Okay, so that was just to explain this a little bit more. And now, how do we write down the enrichment functions? So that is super simple. Basically, what we do is we do the standard part. So we have two parts. We have the standard finite element part. So you can think of that as the polynomial part. If you use IGA, you can think of that as the B-spline part, or the NURBS part, or the moving least squares part, or the radial basics part, or the whatever part, as long as that thing is a partition of unity. You can use any function that's a partition of unity, meaning that these ni's here can be anything that are a partition of unity. So that's very vague. It can be a lot of functions. And then you take the enriched part, which, as we said, we localize using these functions. We call them something different here, phi j with Sunda, but in fact, that thing could be also nj. So that could be exactly the same functions as the ones that you use for the standard FE, but they can also be different. So it is completely up to you. That guy here, psi, is the enrichment function. So that's what you know about the solution. Let's say you know it's discontinuous, you put a discontinuity singular, singularity log r, put log r. Sine x, put sine x. And then you're going to be able to reproduce this, okay? Assuming you can integrate it. Maybe some of you who are a bit astute already thought about difficulties associated with that method. We will talk about it a bit. All right, so then you end up with a discrete system of equation, and as you can imagine, you have the standard part, which is this KSS. You have the enriched part, which is this KSE, and then you have the hybrid part, which is the KES and KSE. Okay, so these hybrid parts are going to be mixed standard enriched and enriched standard. And the enriched part is associated only with the enriched degrees of freedom. The standard part is associated only with the standard degrees of freedom, and the mixed part is associated partly with the standard and partly with the enriched. Okay, and then the right-hand side is simply the standard force vector and the enriched force vector. You put these two together, and you get what's called an enriched finite element approach. And that's all. So the beauty of that is that, again, we have these phi i's, these phi j's here, which localize the enrichment. Okay, so think about it. If you have a one-dimensional problem and you want to enrich, let's say with root of r, this is the enrichment function, root of r. If you have a global enrichment, then you will have finite elements. So in fact, if I enrich with root of r, I have to enrich in both directions. So I would then enrich the whole domain with that root of r, okay, which maybe is not what I wish, because it may be that far away here, I don't need this root of r, because actually I need it only here. So what I do is I take these hat functions, which I'm very used to, and then I multiply the hat function with the root r function. You see, so this root r function can be defined in this element, and in that element I take the hat function which I have here, and I multiply it with this root r function. So what do I get? Well, I get some function which looks like the product of a decreasing function with root r. So I guess, if I'm not mistaken, I should get something which has a slope, which is in the so I hope I'm not wrong in saying that this looks something like this, but maybe I'm wrong. But we have something like, which will be a product of a root r. This is not strictly speaking correct what I drew, but it's the idea. So you will have a root r function times a decreasing function. So root r times x, and on the left-hand side, so in fact this is quite the opposite. Root r times x should look well, I should probably draw it, because I don't know for sure, but we will have something that looks something like this, probably. This is the product of root R with this function and that function, okay, in this element. So, and then outside it will be 0. That's the important part. Okay. Okay, so that means that locally you have enriched functions, and outside you have nothing. You still have these partitions of unity, but not much else. I mean, there are a few caveats, but for now it's enough to know this. Okay, then if you assemble the stiffness matrices, that's what you get. You can easily understand how these things work. So you will have the derivative of the standard part, which are here. Okay, so this is the derivative of the standard part times the enriched part. Now you have the derivative of the standard part and the derivative of the standard part. Then you have the standard part on the right and the enriched part on the left. That goes in that block here. And then you have enriched only points, which are these here. Okay, so this is really very straightforward to understand, I think. Oh, and if you want to prove that, you can do it very easily by simply replacing. If you're interested, it's always nice to do it once. We did it last time, but only for a non-enriched approximation. Just put UH here, and you put delta UH here. And delta UH is exactly the same, except that instead of having U here, you have delta U. Instead of Q, you have delta Q. This delta effectively means W. So if you wanted, you could call this W, and it would be the same. It's with reference to the principle of virtual work. That's why it's written delta. Okay, let's move. So what we can deduce here is that we can add any arbitrary function to the approximation field. And that is the nice thing about this approach. And you can add multiple enrichments. You don't have worries that they collide, because they can collide, and the solution will still be exactly the same. It's extremely beautiful and harmonious and elegant approach. All right, so now the generalized finite element method is pretty much the same, so I'm not going to go through that. The only question is that what we do is that the functions are numerically computed. Okay, so that could be helpful, for example, if you didn't have the analytical solution, but you could compute the solution numerically and then try to derive the solution to your problem using a numerical solution. So, for example, we did something like that with Alexander Menk during his PhD with Bosch. So we had cases where we had orthotropic material, with different alignments of the polycrystal. And locally here, we were looking for the exact solution to enrich the finite element solution. And the problem was that for any arbitrary orthotropic material, we don't know the exact solution to that problem. So we don't know what is the strength of the singularity. We had some r to the power lambda, where r is the distance to the triple junction, but we couldn't write analytically that enrichment function. So what we did is that Alex wrote locally an eigenvalue problem in order to find out what that lambda will be for each combination of of these different material properties here and alignments of the fibers. So every time he has had a different case, he needed to compute that a priori, right? And then once you have this, you can use the enrichment function numerically. You don't actually need to have an actual formula for it. All right, so that's that. It's quite useful. Applications are quite enormous. And now let's see a very particular example for for crack growth. So for crack growth, what happens? So let's say that we are far from the crack. So now the goal is to look at how to approximate a crack using enrichment. Let's say we are far from the crack. So let's say here, in that area. Well, here there is nothing really happening because everything is smooth, the solution is smooth, the crack is far, so we need nothing. So this is the standard path. Okay, that's it. Then we're going to have cases where we start to get closer to the crack, right? And this is what you see here on that slide, right? Because some elements will be split. We discussed that earlier today, and these elements are split because their nodes are split. So this is a node. That node has a support. You remember we defined the word support when we talked about B-splines. This is the set of points where the shape function is non-zero. So this is what you see here. This is the support of that node. The support of that, it's the support of that node because it is a hat function. So you see how it looks, basically, something like that. And so the function is non-zero in that support. So what we say is, okay, well, if the support of that node is split by the crack, because we have this guy here, splitting the domain into two. This is the support of the node is split by the crack. Well, if we have this case, then we say, fine, we are going to enrich this node. And we're going to enrich it with what? We're going to enrich it with this. All right. And why do we do that? Well, because we want a jump in that element. We want a function which is discontinuous. Because the displacement field in that element will be, let's say, in that support will be discontinuous. So if we split it like that and we plot it, we will have a jump. And this is what the displacement field will look like. Okay, so we have a jump across the interface. This is the interface. So if we have a jump, we need to have a jump in the solution as well. And to put this jump, we just simply decide to use enrichment. Now, what do we do about this? What do we do about the crack tip fields? So what do we do about the crack tip fields? We select some nodes enrichment. Right. So the singular enrichment is here for all the nodes that are within a disk. We could explain why that is necessary, but now it's a detail. So we will just enrich within a certain radius around the crack tip. And we enrich with what functions? We enrich with those functions, f alpha. These f alphas are given here, and you see this root r, root r, root r, root r, and you see this sine theta over 2. The sine theta over 2 makes sure that you have a discontinuity across the crack faces, because when theta equals pi, you get sine pi over 2, and theta equals minus pi, sine minus theta over 2, which gives you a jump. So that's exactly what you want. And then you have these other trigonometric functions, which are in fact they are the span of the functions that will generate the first order asymptotic fields close to a crack tip. This is the Westergaard solution, and this is the solution which was derived by Westergaard, which shows you how the solution close to the crack tip u of r and theta looks like asymptotically. So the first term is root r times b to the power b of theta, which are the branch functions, which are these cosine theta over 2, sine theta over 2, and so on. The second term is r to the power 3/2 times some other trigonometric function c of theta, plus r to the power of 5/2 times some other functions, and so on and so forth. And the more terms you put in, the better the solution will be. For example, if you put the r to the power 3/2, you will be able to compute what's called the T stress, which is the term in front of the term r to the power 3/2. And if you put the root r term, then you'll be able to compute the stress intensity factor, which is the amplitude of the function in front of the singularity when you compute the stress close to the crack tip. So for those of you who did fracture mechanics, these things should be rather clear. For the others, please let me know if you're interested. I can give you some references so that you can start reading on that. And so that's how the functions look like. You see that discontinuous function you can see on the left. The singular functions you can see on the right. So you can see that the discontinuous function sine theta over 2, which you have here, looks pretty much like a discontinuous function here, because you have this jump, and here it looks like some sort of root r, right, times the sine theta over 2. So that's the beauty about the method, is that you can put any of those functions in, and that is super super nice. Okay, so now that is how it looks. We have Heaviside functions that lead to a jump. We have branch functions which lead to the singularity. And that's it. And we can do that for any arbitrary cases. We just look for the nodes whose support is split by the interface, and that's it. Okay, so now how do we handle discontinuities in isogeometric formulations? Because obviously it's all nice to be able to do discontinuities. That's why I wanted to introduce all these formulations to you. But we started with IGA, so it would be nice to see how we can handle that. But I think we're getting close to the break, so I won't start a new topic now. I'll just let you go out for a short while. And I think we can maybe start in, I would say, at 15 past, if that's fine with everybody. So it's in 17 minutes. And this way you can breathe a bit. I can have a sip of water. And we're all happy. So I hope it works with you. Katerina, everything's fine? Okay, good. Yeah. It seems to be now working.
Yes, everything is good.
Okay.
So are we gonna take 20 minutes break?
Very good.
Okay,
Yeah.
so we reconvene in 20 minutes.
Yeah, let's say about 11:15 or so.
Okay.
All right. Thank you. A
you.
lot. Hello again. Can you hear something?
Yes, we can hear you, Stefan.
Okay, thanks.
And before you start, I have to make you aware there are 2 questions in the chat.
Oh,
I can read it for you, or let me know.
let me see if I can manage to read. Oops, what did I do? Just 1 second.
So you look like you don't have them. Oh no, no, sorry, my bad. So the first question, they just sent it to me privately.
Okay.
So do you want to answer now or at the end?
No, but let's do it now. It's nice. Yep.
Okay, the first question from Luan says, how sensitive the control point distribution to accuracy of solution? How sensitive is the control point distribution to accuracy of solution?
So how sensitive is, I guess, the accuracy of the solution to the position of the control point, or vice versa? Because it seems, so basically how important it is that we select the right control points. Is that the question?
Not sure. Maybe Luan, can you unmute yourself and explain more a bit? Thanks.
Thanks for taking up the questions. I aim to ask at the end of the lecture, so not to stop you, but yeah, now we can start as well. So when we use the edge refinement, we can control number of control points. So we can have different distribution. For example, we can bias it towards the boundary, or it can be any distribution shape or distribution of control points. How it affect the accuracy of or convergence of the solution?
Okay. So if I understand what you're asking, thank you for the question. It's a very general question, so difficult to answer without knowing what test case we're referring to. But generally speaking, when you will, first of all, in isogeometric analysis, the control points are, in fact, it's an interesting question. So the control points are doing 2 things. One thing is they are defining the geometry.
Yeah.
And the second thing, they are defining the unknowns. So in your question, I see 2 parts. I see one part is if you move the control points, you should make sure the geometry does not change, first of all. And that is possible. So there are algorithms that allow you to increase the number of control points without changing the geometry, which is not obvious that this is possible, you know. So you can add control points, not even talking about making the knot multiplicity increase, but you can actually add actual control points without changing the geometry. So that is doable. We did it. The second thing is that once you have done that, you would need to know where you want to put the control points in order to achieve a certain accuracy level. And to do that, the only way I know to do it properly is to have an error estimate. So to have an a posteriori error estimate, which means locally in each patch, you are going to try to compute how accurate the solution is. And if you're interested in this, I can share with you what we did recently on that, because there is in fact, it's not so recent, there is an old paper on adaptive PHT splines. And I think that would answer most of your questions. And we could then discuss it, because it's a complicated topic. Basically, what you're asking is how to select the points that you use, where to put the nodes, you know, in finite elements.
Yeah, that's the question. Yep, thank you.
Exactly. So the associated question in finite elements is, where do I put the nodes such that my error is minimum? And that is such a huge question that we cannot answer it in general for any problem. It depends highly on the problem. So and maybe we would need to discuss more in detail what problem it is. So for example, if it's a crack, as we had before we were talking about before, then I don't know if you see the screen actually.
Yeah, I can. Yeah, thanks.
Yeah. Okay. So for example, here in the close vicinity of the crack tip, you know that you're going to add more points there because this is where the things happen. You know. So it will all depend on what you want to do. So if you do fluid structure interaction, for example, then you will have we'll have a structure which is embedded in a mesh. So let's say this is the structure, and the flow is going, let's say, around the structure like this. So if that happens, well, then I think intuitively you would want to put more points to describe the surface here, because this is where everything happens. And at the same time, the question is how many points is enough points? And that is what our estimates can help you do. And if you like, we can, I mean, I'm going to talk about something now which is related to this, which is a generalization. Yeah, it's a generalization of IGA, which is called geometry independent field approximations. And I think that is something that maybe is going to partly answer your question. And then what I can do is send you the papers that we wrote on that, and also other colleagues, so that you can have an idea what you can do about the local refinement of these things. So yeah, so there will be basically 3 ingredients. The first one will be computing the error. You will need to compute the error level. Then you need a marking algorithm in order to mark the elements for refinement. And then you need a mesh generator or some generator for the control points, which is not always easy. So the one way is to use the T junctions, as we said before, in the oak tree approaches. So this is clearly one way, right? So you can use this, and this is what we did. But there is a bit of a difficulty, so I'd like to talk about it a bit later today. This is one of the final things I wanted to talk about. And then, then if you like, we can get in touch afterwards and even visit each other to try to discuss this in more detail.
Great. Thank you so much.
No, you're welcome. Thank you for your question. It's a very good one. Okay, Katerine, was there another question?
Yes, there is another question. It says, in terms of computational cost, how efficient using the NURBS as a basis function compared with some spectral functions like a Chebyshev function, if we can use nodes as grid points?
All right, so comparison with spectral methods.
Right.
Okay. Yeah, very interesting question. Again, I don't know how to answer generically. It's going to depend on the problem. So if you cannot compare methods like this in a general way, one needs to look at what problem is being solved. So I guess if it's about Chebyshev, it's probably a wave problem. And if it's a wave propagation problem, some sort of hyperbolic thing. And then if the solution is looking like a combination of plane wave functions, then you can, a priori, I cannot answer the question. I mean, I cannot a priori answer. I don't think this is known. We can just speculate. It wouldn't be very accurate, but if we know more about the problem, then we can try it. I can give just examples. In our case, Chintan Jansari recently in our group worked on acoustic issues for various values for the wave number. So it's Helmholtz equation. I don't know if this is the problem that you guys are interested in that case. Maybe you can tell us more. And if that's the case, what Chintan did is that he did a combination of local enrichment and plane wave enrichment. So he has some, let's say, PHT splines, which is a type of spline. And on top of the splines, he adds a plane wave solution to the basis such that he can reproduce the basic components of the possible waves that can propagate in the medium. So I could show you some results on that if you are interested. In fact, the paper is currently being reviewed, but it doesn't really matter. But I wouldn't like to show you something which is completely orthogonal to what you're interested in. So maybe if you, I don't know who asked the question, but if that person could tell us what the problem is, then maybe we could be more precise in answering it.
Yeah, that's actually me again, and that's related to the previous question. Thanks, Stéphane. Yeah, we can chat later,
Okay,
if possible.
Yeah, it's definitely possible. Let's do that.
Yeah.
This
thanks.
way I can, but now I know that this is of interest, and we can, it's actually good because I'm very happy to see that there is interest about error estimation, because it's not a very commonly tackled field. And I think it's a shame because it has a lot of impact. I mean, in our group, Raphael Bull is working on this very much, on the Bank-Weiser error estimate. As we said before. If that could bridge the gap between the two crack faces, and that could allow forces to be transmitted from the top to the bottom or vice versa, such that you have still some transfer of stress across the crack faces. And if you have adhesion properties, or if you have glue that's used for composites, for example, that could be also a nice way to model these things. So if you do that, then you see also that there is a nice advantage, because if you have a traction-free crack here, sigma goes to infinity. So the stresses go to infinity when R goes to 0, meaning the distance to the crack tip goes to 0, the stresses go to infinity. When you have a cohesive crack, the idea is that you regularize this infinite behavior at the crack tip by closing the crack faces using some sort of traction separation law, which allow the cracks to, instead of closing in an abrupt way, to close smoothly, like for example this way. And because they close smoothly, you don't have this singularity at the crack tip. It's a bit like having a blunt crack tip as opposed to a sharp crack tip. And so by introducing these cohesive cracks, by the way, you can read the original papers by Dugdale and also by Barenblatt. So those are the original papers. And then you have a lot of papers by Needleman on that, for example, talking about initially rigid interface elements and so on. So though that is a very heavily trodden area, which you can read a lot of papers about. It's super exciting. It's very beautiful. It also allows to put nonlinearity in the fracture process. As long as you have a traction-free crack, everything will remain linear, and you will have singularities. This is not very physical most of the time. So having these sorts of cohesive laws allow you to model not only brittle fracture, meaning cohesive cracks, but also quasi-brittle fracture, where you don't have only traction-free interfaces, but now you have some sort of cohesion, which is maintained through the fracture process, and that happens in quasi-brittle materials, such as, for example, concrete or certain types of composites, depending how you make them. Okay, so that's what you need to do. In order to do that, well, you recognize this weak form. This is the body force. This is the traction on the Neumann boundary. This is a divergence of the stress. So basically, what we had before as grad U, grad W. This one here is the W U prime, and this one here is the B W. Right. So this is the equivalent in the notations that we had before, so that you can recognize it. On top of that, you have this integral over gamma D being the surface over which you integrate, of the jump. So this double bracket means jump typically. So this delta that you have here, this is the jump in U. So the jump in U gets as an input, and you get the tau as a function of the jump in U. Then you simply evaluate this. You have to linearize it, because this is a nonlinear function, obviously, because, well, maybe it's not obvious actually, but this U is an unknown, because the solution enters in the calculation of the jump. You need the solution to compute the jump. So you have that type of non-linearity when a function in the problem depends on the solution itself, right? So this is a function of U, and U is unknown. So therefore, this is a nonlinear case. You can linearize that using a consistent linearization that you do in plasticity as well. It's very similar. This is, yeah, very similar. So it's basically variational inequalities as well, similar to contact. Okay, then you can choose the basis functions that you want, and you can introduce discontinuities directly in the basis function. So this is what is done by Verhoeven, Clemens, in the Netherlands with Tom Hughes in 2011, and by Nguyen Vinh Phu and ourselves in 2013 for 2- and 3-dimensional composite delamination. So you can find this paper in Composite Structures. And what's cool is that, when you look at that, you can, by increasing the repetition of the knot at 0.5, you can create, as you can see, a kink in the solution. right? And by increasing it even, yeah, that's it. So this is the knot vector that you need. And then if you look at the jump, you know, this is the derivative. So this is u, and this is epsilon. So you see that you have a jump in the derivative, right? So that allows having material E1 on one side and E2 on the other side. And you put these two together, then you have a jump in the derivative, in the strain, essentially. And when you want a jump, not only a kink, but now a real jump in the function, well, you simply increase the multiplicity again. You just add one more 0.5 here, and you automatically put a jump in. So when some threshold is reached here, what you do is you add an extra point so that you have a multiplicity of the proper order. And that is going to allow your method to reproduce these discontinuities. And I think this is really cool, as long as you know where the interface is. If you don't know, then this is less cool, because obviously you cannot just let these things propagate arbitrarily inside the domain. However, in a case that I showed last time, so I'm showing that again just for you to fix your ideas on these, you can see the extremely nice results here. Okay. All right. So this is the the example that we talked about. We have an initial delamination here. Again, you see this works well because you know where the delamination is. But look at this. Right. There's always there. Yeah. So this is not we can discuss it later. Something really important. techniques which can be used readily if you are interested in it. Not for IGA, but for other estimates. So feel free to contact us about this, and I'll put you in touch. And I think that is something that probably can be helpful. So now we're not talking about a priori error estimates. So if you remember when we talked before about error estimates, I told you something like U minus UH in a certain norm is less than or equal to C to the power of H to some power alpha. But this is a priori. It means before you solve. A priori means before. Okay, having an a priori on something means having an opinion before figuring out what it's about, which is a common thing to do when you're a human being. You have a priori about many things, and then you experience it, and then you have a posteriori experience about it. And this a posteriori experience is usually different from the a priori experience. For example, you never talk on stage. You go on stage once. Before going, you had an a priori feeling, which was very negative typically because you're very scared. And then you get on stage, you start talking, and then you think about what the experience was like, and you think, oh, finally, it wasn't that bad. So you change your a priori vision for an a posteriori vision. And this a posteriori vision, in the case of error estimates, is so before computing. So before computing UH, so it means you do not know the finite element solution, right? You don't know what it is, but you know that if you computed it, it would satisfy this, which is absolutely super strong. And that is what other methods like collocation methods, for example, don't have usually. They do not have this a priori estimate. It's quite difficult mathematically to analyze these collocation schemes because they do not rely on integrals, and the norms are much more difficult to deal with, but it's much, yeah. Okay, so now the a posteriori error estimate is this is after computing UH. So already the a priori thing is quite a feat. It's quite a remarkable thing that you can say, I don't know U. I don't know the exact solution. I may know it's discontinuous, but I don't know what it is. Maybe I know vaguely in which space it is, but I don't know what it is exactly. I also don't know UH. I just know based on what space I will build it. So I know it's polynomials, I know it's B-splines, I know it's NURBS, I know it's RBF, I know it's MLS, I know whatever, I know it's space. I don't know what it is exactly. I know just the basis functions. And although I don't know either U or UH, I can tell you that the difference between the two is less than something. It's remarkable, right? Because you don't know anything really. So this is something, I think we should not stop being amazed by the beauty of this. The second thing is the a posteriori thing. So this is probably not much less beautiful, but it's a bit different because now you do not know U, so that's no idea, but you do know UH, so that you can know, you just computed it. And so what you'd like to do is to give an estimate of the difference between the exact solution, this is U, and the thing that you just computed, but you don't know it, the U. So how do you do it? That's the whole point about error estimates. And in a question that was extremely astute and clever that was asked before about where do you put the control points, this is exactly what you're trying to answer, because if you know that in your domain, this is the domain, and you know that in some area, let's say that you have, let's just make something interesting, like, you have an inclusion of that shape, you will start solving, and then here you will see that the error is huge. The error is large. So then naturally you will want to put more points in this area. because if you do, then you hope that you will control the error much better. But if nothing happens in that area because everything is sort of smooth and the solution is regular, then you can use very few control points or very few nodes. So that's the idea of a posteriori error estimates. You know UH, you do not know U. And there are a huge variety of these things. You could think, and I'm not going to tell you all about them, but just a bit. So again, if we think back at one of the first slides that I showed during this whole course, this is the discretization error. This is what we are interested in. And this is the way that you do verification. And again, I was revising a paper yesterday where one of our students, although we keep repeating constantly that verification is the discretization error and validation is the model error, was using validation as opposed to verification. So this is something that here we're not talking about the model. We assume the model is just fixed. This is known, this is, for example, Laplacian U equals 0. That's it. Laplace equation plus boundary conditions. That's the model. That is here. It is known model error 0. We just care about how accurate the solution is. And we want to compute U minus UH, not knowing U. So not so simple. So how can we do that? So that's the basic idea. Okay, so let's assume that we have the reality. So the reality is this guy here on the left. This is this beautiful, whatever it is, container. Then you model that and you say this container is exactly cylindrical here. So the geometry is exactly cylindrical. The roof is exactly a piece of a cone, and so on. So I make huge assumptions on the shape. I say this is an exact cylinder. Obviously, it's not, because you never can manufacture anything exactly. So this won't be a cylinder. The cone won't be a cone. The reinforcements won't be the same shape that you think they are, and so on. So you make a lot of errors. You say this is aluminum, let's say, and aluminum grade, whatever, with Young's modulus, whatever, Poisson's ratio, whatever, all that's wrong, because you have no idea what these things actually are. So you can have ballpark figures, plus or minus 10%, this is right. But then if you don't want to do stochastic simulations because it's too expensive, you just have to select something, assume it's correct, and start assuming that this is the ground truth. So this is fact. And then you say, fine, I'm going to discretize. So I'm going to build a finite element mesh, and I'm going to solve. I'm going to solve with one mesh, and I get the discretization error number 1, and I'm going to solve with another mesh, and I get discretization error number 2. That's it. So what you can do is you can first solve a super dense problem, super fine, and you say, okay, this is my reference solution. I'm going to use that as a reference, and I'm going to compare my coarse solution to the refined solution. And that's going to tell me about some error level. Okay, now I'm not going to go through the two equations that are written here because they are not so important, but I would like to tell you what you can do with such error estimates. This is the work that we did with Cineiro in Belgium, where we implemented an error estimate for, in that case, XFEM. And this is with Olivier Pierrard. And this is an XFEM enriched. This is a CMAME paper, which I can give you if you like. It's, I think, very convincing as to why error estimates are useful. So this is a beam. It's got a notch, a pre-crack at the top here. And it's got a hole here. The hole is going to act as an attractor of the crack, because the crack is going to tend to want to go to the hole, because that's what cracks do. They try to reach free surfaces. So that surface here is going to make it easier for the crack to propagate. Therefore, it's going to propagate in mode 1, because that's what it likes best. That's the easiest thing for it to do, propagate in mode 1. So it's going to curve, try to reach mode 1, and eventually hit this hole. So this is what you see. This is a pre-crack, which is a quarter penny crack, which is typical of what you use in the aerospace industry. You usually put an initial crack, and you try to measure how many times, how many cycles that crack can grow before you end up with total destruction of the component. And well, as you can see, with local refinement, you can solve the problem with about 300,000 elements. And just so you know, if you do not use mesh refinement, this probably will partly answer the question that you were asking before, which I thought was very sensible. If you do not have local mesh refinement, then it means that you need to predict before the crack propagates where the crack will propagate, which by definition you don't know, because otherwise you wouldn't be solving this thing. And so you would need to refine like crazy this whole region with extremely small elements, and then let the crack propagate, hoping that you have enough elements. So this is a bit brute force, honestly. And this is unfortunately what is done in industry on a daily basis. Adaptivity is barely used because it's a bit tricky, a bit complicated to get used to. And a lot of the codes don't have the capacity to do this, although it does exist. So that's why we were very, very happy to implement that within this commercial code called Morpheo Crack, which is developed in Senairo in Belgium, not far from here, in Charleroi. And so if you didn't do this, then you would have to really take care of having a huge number of elements. So you can see it on this picture. So this is what happens if you don't do anything. So you just assume that you put elements everywhere just in order to be able to have a chance to capture the crack. So it's really not efficient because you have here millions of elements, and this is not an overstatement. I think here it's maybe 2 million or something. So 2 million as opposed to 300,000. So it's a factor of 6 to 7. So almost 1 order of magnitude, and we could probably do better than that. So that means that by computing the error on the fly, you are able to have a much more efficient approach, right? So this is clear. On top of that, with our driven partner in Strasbourg, Stéphane Bordas and his team, Mimesis, we developed with Fouk, who is now working with for ANSYS, the commercial software company. Fouk developed a real-time error estimate also with Satyendra Tomar, and so we did that, and that allowed the local error to be computed in real time. So what you see here is someone playing with a beam and deforming it in real time with a joystick. So basically they are deforming the beam, applying forces on the beam, and as they apply forces, you see local refinement taking place inside the domain. So this was one of the, I think it was the first real-time error estimate that had ever been published. And I believe that is super helpful because as you see, you turn this beam, you see the number of elements increasing, and then when you unload, the elements come back to the original coarse mesh. And that is, I think, something which can be really applauded, because this is also return to the future, because that's the video I showed you on the first day. In order to motivate the fact that we had to think about geometry and to think about how locally we were refining the mesh. So this is the work of Fouk, again with Stéphane Cotin in RIA, in collaboration with ourselves and Satyendra Tomar and Franz Schuli and other colleagues. in France. Okay, so similar work was applied in order to solve the problem of needle insertion in the brain. And to do that, you see here a very simple toy example where you insert the needle, and as you insert it, locally you compute the error, and if the error is too large, boom, you refine. This is a simple one. And now we try to introduce a needle in the brain, and the idea is that we want to reach a certain target, which is hidden from view. And as you insert the cannula, and then you retract the cannula and you leave the electrode in place so that this area of the brain can be stimulated, you would like to make sure that you commit the minimum amount of error, and which this error estimate can guarantee. So yeah, that's it about error estimates. If you want to know more about that, I can give you a few pointers, and I can tell you briefly how, what the logic is behind these error estimates. So well, in fact, maybe the easiest is to do that here. So normally you should see a black screen now. I hope you see it.
Yes.
Yeah, thank you. All right, so just a brief explanation as to what it means. Here we are talking about a posteriori, and so it's impossible for me to introduce that in detail, but I just want to give you the general ideas so that when you read the papers, you have a superficial, at least, understanding of what we're talking about. Again, what we're doing is we are computing the error between the exact solution, U, and the numerical solution, UH. And we are computing that in some norm. And the goal is to see where this is going to be high. So the goal is to have a map of, let's say, E is high here, and E is low here. Okay, low, high, and E, let's say, medium. Okay, so that is like the very basic way of thinking about it. Where is the error high in the domain, and where is the error low? Again, things like L-shaped, you will have high error here, so you would like to refine here. So that's the first thing. You have to figure out where to refine. And in order to figure out where to refine, the question is, how do you compute the difference between U, which you don't know, and UH, which you do know because you just computed it? Well, so there are two ways. The first way is called residual based, let's say, residual error estimates. So you remember, we solved the problem which is Laplacian U. Let's imagine plus B of U. I'm just going to equal 0. U equals U bar on gamma U, and grad U dot N equals Q bar on gamma N. So this is the Neumann condition, this is the Dirichlet condition, Neumann condition, and this is the governing equation. So let's say that we solve that guy. So U here is the exact solution, so we don't know it. And if you remember, I told you about the method of weighted residual before, right? And we said what we do is we take Laplacian U plus B of U, we take all that stuff, we multiply by a test function W, and then we do integration by parts. Okay, and that will give us integral of grad U, grad W plus integral of B of U W equals 0, and there will be a term that comes from plus integral over gamma n of q bar w d gamma. Okay, so this is just a quick recap. So again, here everything is the exact problem. Here it's just a weak form of exact problem. This is the residual of the exact problem. So what does it mean? Well, it means very easy, is that, well, the residual is that guy. Okay, so inside the domain, so if you remember what we talked about when we said something about collocation, we said there are essentially 3 domains: the Dirichlet boundary, the Neumann boundary, and the interior of the domain. So Neumann boundary, for example, could be this. The Dirichlet boundary will be that, because it's the complement. Oh, sorry, wrong color. Because it's the complement. So that is the Dirichlet boundary. And now that thing is the interior, omega. Okay, gamma n, gamma d. Gamma d or gamma u. Let's call it gamma d. As Dirichlet, it's also the essential boundary condition. So we know all that stuff. So depending if we are inside or outside, we will have different types of elements. So we will have elements that are only inside. We will have elements that are inside and on the boundary, which is the Dirichlet boundary. Elements which are both inside the domain and share an edge with the Neumann boundary, and we will have some sort of very hybrid elements that are at the interface between gamma d, gamma n, and the interior of the domain. Maybe that could happen. And then what is the idea of a residual error estimate? So, well, the idea is very simple. It's the first thing to note is that we do not know u. We do not know u, but we know uh. So what do you do if you have uh? Okay, this is the solution. You know the problem you're supposed to be solving because you just wrote it here. So what do you do if you have uh and you want to know if it's accurate or not accurate? Well, the most logical thing to do is to just plug in uh inside this guy, right? Because if you plug it in, you're supposed to figure out whether yes or no the residual is high or whether the residual is low. So if you satisfy the equation more or less, then you think, okay, it's more or less, it's more or less okay. If you satisfy it very well, then you say, oh, the error is low. If you satisfy it not at all, because it's very bad, then you say, okay, well, the error level is very high. And one problem with that, but that's getting a bit into too much detail now, is that if you plug in exactly the same solution as the one that you started from, you will get something close to machine precision, because that's by definition the equation you just solved. So you need to try and be sure that the solution that you plug in is from a coarser space in a certain way. So this leads to difficulties. But anyway, let's not worry about that at the moment. Let's just imagine that you have one element which is like so. You will have elements that are maybe like this, that share elements with edges with the boundary and edges with the interior, and you will have all sorts of different element types. And what you're going to do is you're going to build another field inside these elements such that you can compute the residual inside each element. So that means here I want to compute something like Laplacian of UH plus B of UH. Okay, and that will be the residual. You want to compute something like that, and skipping a lot of important points, but this is the idea. So you want to plug in your solution and recompute inside this guy the solution. Okay, But if you do that, let's just imagine very quickly that we did this. UH, let's say, is linear. You know, let's say that you use these shape functions. If you plug in a linear field and you take the Laplacian, you get what? 0. So that's not cool, right? Completely useless, because you will get in here some 0. Okay, so you think that your solution is super nice. In fact, it doesn't mean anything. It just means that you're plugging a linear function in a second order operator, so you get 0. So not nice. You will get some stuff that you don't want. So don't forget that you are also within this element. So you will also have the fact that you are within one element and the other elements are forgotten for some time. You have also the flux. So grad q dot n along the boundary that you should not forget. So this is basically one type of error, let's say an idea behind what you do in residual error estimate. So this is by far not precise. This is not the goal here. It's just to give you an idea. So the principle is you measure how well you satisfy the equation that you solved at the beginning. So in your question before, you said, okay, how do I know where to put the control points and how many control points to put down? Well, the answer is, I don't know, because it depends on the problem you solve, first of all. It also, but a way to answer the question is to use an error estimate. And if you use an error estimate, you will be able to really make a sound decision as to yes or no, should I refine, and by how much. Okay. So again, there are some extra difficulties, because once you have computed the error in the domain, let's imagine that you have done that. So you have this domain, it's a beautiful domain. Then you have all sorts of elements in here, and I'm not drawing all of them contiguously because it takes too much time. But let's imagine that you have those elements. And I don't know, maybe in what you will do is you will compute the error in all these elements. So you will have an error here, E2, E3, E4, E5, and then you're going to order them in terms of error level. So for example, you'll say, okay, E5 is less than E1, is less than E3, is less than E88, is less than E77, is less than E48. And then you order all of those, and then you find the one that has the smallest error, and who knows, maybe E99, actually let's take something else, E9, let's say, has the highest error. So what you do then is you need to mark the elements for refinement. So you can say, I will only refine the elements that are within this range. You know, so I say, okay, within that range of error, let's say E3 is more than 10 negative 2, less than E88, less than E77. All you're going to say, okay, I'm greater than that threshold. This is a threshold. So I'm going to refine all the elements that have a higher error, and that's it. And you can also decide to coarsen certain elements. Okay, so that's called the marking strategy, and there are as many marking strategies as there are people doing this sort of work. So you can come up with your own. And once you have done that, you refine the mesh, and that is then done either by mesh refinement or by moving the nodes. It's called R adaptivity, like relocation adaptivity, like when you move house. All these nodes actually move houses and move around, but you don't change the number of nodes. You just relocate them. Or you can use edge bisection when you split, the elements into two, right? So that's the basic idea behind this. And or you can use P refinement and say, okay, I don't like what I'm seeing, so I'm going to increase P and see what happens. Okay, so that's the first way you can do error estimates, and it's called residual-based error estimates. That was a very, very cursory introduction. The second, which is going to be also cursory, is called recovery-based estimates. And by the way, when I say estimates, it's an abusive notation because typically it's an indicator, which means that whatever I compute is not necessarily converging to the exact error, but that is a little bit too detailed for now. So let's forget it. A recovery-based error estimates. What does it mean? Again, the idea is you want to compute u minus UH in some norm. And this introduction you will see is useful. I will be done in 8 minutes. Afterwards, I will show you how you can use that in practice. Okay, so you want to compute u minus UH. Remember, u is unknown, but UH is known. So in a recovery-based estimate, you make one assumption. You make an assumption, which is that UH is less smooth than U. That's basically the first assumption. Let's see what that means. Let's assume that you solve a finite element problem on a bar. So it could be the Laplacian that we had before. Doesn't really matter. So you solve that thing and you get a solution. And the solution is going to, first of all, let's plot the exact solution. So the exact solution might look like something like this. Exact solution might look like this and like that, for example. And then what you're going to do is you're going to say, okay, I split this domain into subdomains, and I use my favorite shape functions, could be Lagrange, could be B-splines, could be whatever. So I apply finite elements. And as we know, finite elements are interpolatory, so I will be, if I try to, let's say to interpolate, I will be somewhere on the curve, right? So this would be a happy end if I could do this, right? So yeah, let's say that here I get to there, and here I get to there, and here I get to there, something like that. So what do I see? So this is U, H, and this other guy is U, and this is the exact solution, okay? So the exact solution is U, and the other is UH. Okay, very, very, very simple. So what I assume in doing this recovery-based error estimates is that the exact solution is always smoother than the finite element solution. And in fact, it's true, because if I take the derivative of this finite element solution, what do I get? So let's imagine that I want to compute the derivative. So I will call it epsilon h, right? So the derivative is the slope of that. Okay, so here we have a certain slope. Here we have another slope. Here we have a negative slope, which is pretty large. Now we have almost a constant slope, which is almost 0. Then we have a positive slope, which is, let's say, something here. And then we have a negative slope, which is somewhere here. Okay. So that is epsilon h. That's the derivative. So epsilon h equals, in that case, du h dx. And this x is the direction in that direction. All right. Okay, so why is it that this is important? So now, clearly, UH is less smooth because U itself, the blue curve, if it's blue, I don't know, this thing is much smoother. It doesn't have kinks, therefore it's smoother. So that's a fact. Okay, so in that case, I'm right. UH is less smooth than U. And now, how am I going to decide whether the solution should be refined, if the mesh should be refined or not refined? So in recovery-based error estimates, what you do is super, super simple. You measure, what do you measure, you think? Well, you measure the size of the jumps. You measure how big these steps are. And if the steps are big, as is the case here, for example, then you say, probably the solution is not that efficient, not that correct. So I need to refine this thing. So that's what you do. You just measure the jumps. Very simple. So you measure this and you say, oh, this is big. You measure this, oh, this is big. Therefore, in the next refinement step, I'm going to add a node here in the middle. And let's assume that we do this. So we go there, we look at the curve, which we don't know, and we see, we compute, and we say, okay, well, now the jump is a little less. Okay, so, you know, I have a negative slope here, but it's quite small. So my new jump is this jump. And this jump is much less than the original jump, which was that jump, right? So now I have smaller jump. And that smaller jump is good for me because it means that the error will be less. Okay, so very simple. But now you're going to tell me, man, you're very nice, but you're asking me to compute essentially jumps, differences between u and UH, but I don't know u. So how can I compute the difference? Well, what you can do is you can build a new function which looks like u, not u, but this u, which looks like u and is built directly from UH. And that is the beauty and the elegance of that thing, is that it actually works. It's unbelievable. So what do you think you could do? So you start with UH. This is this very full of kinks thingy, which you don't like. You know, this guy here is really bad because it has all those kinks. So it has all those kinks, and you're thinking, okay, I don't like that at all. I mean, it's really, really ugly, and I would like to have something smoother. And in fact, I don't care so much about the curve itself, u, h. I care more about the one that I was drawing before, which is this these derivatives. That's what I care about. So what can I do to build a derivative field which is better than this staircase? Because if I can do that, then instead of computing u minus UH, maybe I could compute gradient of u minus gradient of UH, which will tell me how jumpy the solution is. It's some sort of norm of this, right? So that would be du dx and minus du h dx. I can compute a norm of that stuff, then it would be cool. Unfortunately, I don't know this. So this is no idea. This I know because I know UH. You know, I know UH equals sum of ni of x u I. So I can interpolate inside the element using the shape functions. I can do all that stuff, so everything's fine. But I don't know u. So I don't know u. You are unknown to me. U is unknown to me, actually. So u is unknown to me, and so I don't know u. What can I do? Well, what I can do is I can say, okay, how do I start from this curve, which is a jumpy thing, and how do I make it less jumpy? So you have a staircase, you want to make it less staircasey. Well, I have an idea. I can just take the middle points of that stuff, you know, and I can just link them up together to make a continuous function. I have a discontinuous function. What I can do is I can now make a continuous function out of it by simply linking them together. That's possible, right? Nothing and no one prevents me from doing this. And I have now a function which is C0 derivative of UH. Okay, so this is not the derivative of UH, but it is a smoother derivative of UH. And this is what we're going to use to substitute for this grad U. So instead of computing the difference between the derivative of UH and the derivative of U, which we don't know the derivative of U, we can say, all right, what I'm going to do is I'm going to assume that there exists another function and I will call it UH star, which is smoother than UH. And so you can think of it like I'm going to build a gradient of UH, which is smoother than the gradient of UH. So I'm going to call it gradient star of UH. And that gradient is simply going to be this gray curve, which I have plotted here. So if I look at that again, so I have this gradient. I just look at this gradient. This is a smooth gradient, and I simply compare the smooth gradient to the real gradient of UH. So what I do is I measure something like the difference between these two. So I can integrate it over the domain, for example, and it will give me an idea of how big or how small the error is. So this is one way of doing this. So you see the idea again, and I'm 3 minutes late compared to my schedule, but it's okay. What we're going to do is what we want to do originally, let's do it again. We want to compute U minus UH. And so we're going to say, okay, let's compute the gradient of U minus the gradient of UH, because this is, after all, what we are interested in knowing. How do we do that? We need the gradient of U, which is the exact U, but we don't know U. So we cannot compute the gradient of U. Instead, we will say, we will build a new solution, U star, which is smoother than UH, that one we know, and we will use this U star as a surrogate for the exact solution. We will use this U star as a substitute for U that we don't know. So you see, effectively, if you want to remember that in one sentence, you are computing how inaccurate or how jumpy, how discontinuous the gradient of UH is. And to do that, you compare the gradient of UH to a smoother version of the gradient of UH, and you say, I compute that along the whole domain, and where that stuff is too large, like here, I start refining and I add more points, and I do that one step at a time. So I hope you understand. This is a very, very, very superficial, absolutely not rigorous way to think about, to approach that problem. But I hope at least that as a user, it will give you an idea of what is going on behind the scenes. And then if you want to develop these estimates or indicators, they are not so difficult to implement, actually. Similar for the residual based. And please don't hesitate to contact us for that. So now I'm going to show you how that stuff can be used within an IGA framework. And that is something that's not easy, actually. So again, Chintan in our group with Elena Atroshenko has been working quite a lot on that. So I will show you some results which in fact do not come from him yet, because this is very new. So we haven't had time to prepare many presentations on that, but yes, that's it. I would like to show you how this question of local enrichment, or let's say local refinement, can be done in IGA. All right, so I'll show you why there are some difficulties. And once I've done that, you will probably understand very well why the literature is going in the direction that it's going. Once again, we start by, yeah, it's okay. We look at IGA again from the beginning. So let's try to loop the loop and go back to where we started at the beginning of this course. All right, first thing, we talked about NURBS. We said NURBS are universal functions. They are the industry standard, but they have some difficulties associated with water tightness, lack of local refinement, and so on. So you realize here, I already was telling you at the beginning, although we had not talked about anything, really no local refinement. This is not exactly true. You can do local refinement, it's just not made for that. So the question you asked before is absolutely relevant, because you're asking, how do I decide where I put my points? And it's not only I need to compute the error estimates, that would be one thing, but no, you need also to know where and how you should put the points in. It's not only computing where you should put them, you should also know exactly how you can do it. So that is why there is even a question here. And the question was really, really excellent, because it's exactly nailing one of the difficulties. Now the T-splines, what do we do with that? Well, T-splines look like T's. So as we said before, T-junctions are very useful because they allow you to do things like this. You know, you have a regular mesh and you can locally refine using quad tree approaches. Okay, so for example, I could add another T-junction here, and then I could go on, making sure that I don't have too many hanging nodes. Okay, then there are advantages, drawbacks, as usual, to T-splines. And subdivision surfaces, very nice, watertight. So the guy here in Jerry's game will not leak, which is always good. It's flexible. It can be used with 3D printing. It has low water smoothness and so on. So that there are drawbacks because that's not very smooth, but it's got other advantages. And then, you know, there are humongous numbers of other splines. So just to name a few, PHT splines, this is what Chintan is working on. You have LR splines. And then recently U splines, which are developed in the US by Mark Sederberg and others. So yeah, there are many spline types. And the idea is that you want to find the right spline type for your problem. But then you're going to tell me, Stefan, you're losing your mind, because you're telling me that you want to use NURBS for the boundary of this, because it's very, very nice. And you just told me that all you know, people from the CAD world are using, when they are drawing the teapot like I'm doing now, they are using these fancy NURBS objects, which you spent hours introducing painstakingly using 1D examples. And then I'm telling you, yes, I agree, these are NURBS. And I want to locally refine. Unfortunately, people in the design world use mainly NURBS, but NURBS are not very well suited for local refinement. So then I'm telling you, maybe you can use T-splines, which are used commercially, but much less. Or you can use PHT splines, which are probably not used at all commercially, and LR splines, which are probably also not so much used, and U splines, which start to be used. But okay, how do I reconcile the two? Because I have, you know, the guy drafting the thing sitting on his chair, and he uses NURBS. So this is the designer. But then the analyst here, the person there wants to use PHT splines, maybe because they want to do local refinement. So I have someone giving me NURBS as input, but this analyst here is telling the NURBS guy, well, it's all very nice that you're giving me NURBS, but I would like to refine locally, and your NURBS are not so well suited for that. Although I can do it, but it's kind of long. So I'd like to use PHT splines. So that's why we developed an approach which is both using the NURBS curves, as you can see on this slide, for the boundary and the geometry of the domain, but instead of being restricted to use the NURBS curves also for the approximation all the time. Sometimes it's very useful. For example, in dynamics problems, NURBS are super well suited. In fluid mechanics, they're also very well suited. For certain advection diffusion problems, they avoid these jumps. So, well, instead of thinking about that, I'm going to use another approach. And I'm going to use an approach which we call the geometry independent field approximation, or generalized isogeometric analysis, which was developed by Satyendra Tomar, Gang Shu, Elena Troshenko, and myself, and also by a team, which I will mention later, of Gernot Baer, who is now emeritus professor in Australia. And here is the idea. Okay, so that I will let you read later. Just in case you want to know if you have our papers on the field, you can take a screenshot of that, because that will give you a very clear, let's say, description of the various works that were done in that area, including Nietzsche's method, which I didn't have time to cover, unfortunately. So take a screenshot of that, look up the papers, and they will give you a few references. Okay, so now let's get to the meat of the question. We would like to do local refinement. On the left-hand side, you have IGA. This is tensor product. You remember you have a function of x and a function of y, and this is the tensor product. If you have a three-dimensional NURB, you have bx, by, bz, bz, right? Here you would like a T-mesh, something like T-splines or PhD splines, for example, so that you can do local refinement close to the area where you actually know that everything is happening. Maybe a crack is here, for example. And you'd like to do that in a, say, a flexible way. So again, you can take a screenshot of that if you want to have the papers, because they are supporting exactly what I'm saying. And here is the team of Gernot Baer that I was mentioning before, and Thomas Peter Fries, who is now in Graz. And so, yeah, look at this and you will understand the details if you want to. The paper is also can be downloaded here, so you can just type that in your browser if you have time to do it, or take a picture, and that will work. And the question is, how can we benefit from the IGA concept, which means keep the NURBs where they are useful, so NURBs for designers, and use any other splines or any other function for that matter for the approximations. So that was one of the questions. Okay, so let's look at that. We have 15 minutes left, and that will be the end of the course. In isogeometric analysis, you do remember the concept of physical mesh on the right-hand side, the parent element, and the parameter space on the left-hand side. The idea, again, is that we have also an isoparametric representation here. All right, okay, because x is the position of a point. You remember when we talked about isoparametric methods before? We said we have an element, we would like to interpolate the value of x inside, knowing the value of the positions of the 4 points around the rectangle, right? And we say we use the shape functions simply in order to write x, which is what we do here. And then we said, similarly, for the displacement field or the unknown field that we are interested in, you will interpolate what's going on the boundary, and you will get that. Okay, so that's what you're going to get. And now you want to have u inside at point x, let's say, same point as here, for example. And what you do is you use exactly the same map, right? So you use exactly the same map. So this is why this thing is isoparametric. Okay, simply because you use the same mapping for the position as you do for the unknown variables. Okay, next. Now, what do you do in PHT splines? Well, you do precisely the same thing, except that you don't have NURBS anymore, but you have PHT splines instead. And those PHTs are cool things because they allow you local refinement. You see here you have a T junction, here you have another T junction, and so on. So this is the idea of PHT. I mean, this takes some time to describe how to compute them. There are also many drawbacks to this method of PHT, but okay, it's nice. And it starts like PhD, so you know, if you're a student, it can be motivating too. Okay, so now what is this geometry independent field approximation, which we call GIFT, which in German means poison? It's not a very fortunate choice, but hopefully this is not the poisoned pawn like in chess. Let's be careful about what we're doing here. So we have a certain approximation for x. This is using NURBS, but now for the fields, we are not using NURBS anymore. No, we are using PHT splines. So we do not have this isoparametric mapping anymore, which is why people initially thought that the method would not pass what's called the patch test, which in effect is an interesting concept, but is not necessary nor sufficient for convergence. At least it is still debated as far as I know. So we did a few tests, a few meaning 72 tests of patch tests, depending on what the value of P and Q were for both NURBS and PHT splines for various cases, and we will see what we find. So for IGA, which is the standard NURBS isogeometric or isoparametric way, you get certain solutions, which you see here. And for the GIFT part, as you can see, the solution is pretty similar on this fishy domain for the Poisson equation. Poisson in French meaning fish. You have some nice curves and some nice properties, and you can locally refine, which is exactly what you wish. This is what you see here. So now we would like to have some conclusion. So here are a few of the examples that we ran for the patch test. So that was done with Gang Shu, mainly Elena Troshenko and Satyendra Tomar are responsible for these very nice results. We looked at different types of geometry parameterization and solution basis. And for various cases, we looked at the patch test. So when we have a dash or a click or whatever this shape, it means that we pass, otherwise it means we don't pass. So we see that we have certain cases where we do not indeed pass the patch test, as was predicted by reviewers of the paper initially. So that was an instance where actually the reviewing process was very useful and took 2 to 3 years. So it was very fortunate to see that although we did not pass the patch test, we did get experimentally, we cannot prove that, that's a problem, we cannot prove, but we get optimal convergence. What does it mean, optimal convergence? Remember what we said before, U minus UH, the a priori error estimate, Well, we have this CH to the power alpha. It means that we get the proper alpha. This is what we mean by optimal convergence. It means that the theory predicts an alpha, maybe quadratic, for example. So alpha equals 2, quadratic convergence, and we do get quadratic convergence, for example. And we do get that in all cases. So there is not a single test case which we ran where we did not get optimal convergence. So we believe that means that the method is not completely useless. It may even be useful. And in cases where we applied that, we really have the following advantages, which I believe are significant. First of all, we use the same basis functions in CAD. So we use the NURBS, which means the guy behind the computer can, or the lady really, can use the same shape functions as they want in order to describe their geometry. So they can build a very nice conic section and so on using NURBS, and we won't complain. That's absolutely fine. And they can pass these NURBS to the person doing the analysis on the other side with another computer, probably a bit bigger. And they pass that, but then this person can now say, okay, now I want to use PhD splines for the analysis, although what I was given was NURBS for the geometry, and nothing prevents that person from doing this. So again, we have the advantages of IGA, which are super useful. Geometry is exact at any stage of the solution refinement process. We do not modify the geometry. It stays what it is. But as you were asking in your question very smartly before, we can locally enrich by adding points at the right place based on our estimators, which I cannot show today because it would take some more time and I don't have it. But now, if we compare the solution per degree of freedom, we see that we are higher, but of course, there is no free lunch. As usual, we have a higher computational cost per degree of freedom because of the bandwidth, because the bandwidth that we have is higher. That's the drawback of the method, albeit small. So again, we have no proof. No proof means that we are not mathematicians, at least I am not, and Satyendra is, but I'm not. So we cannot prove at this point what we have observed experimentally, numerically. But the degree of the solution basis can be increased or decreased without changing the degree of the geometry, right? So we can use isogeometric, which means same order for geometry and field. We can use super geometric, which means the geometry is more refined than the field, or subgeometric, which means the opposite. And when we also showed that for various geometries, using B-splines or NURBS actually did not lead to significant differences. All right, so then what type of problems did we solve with that? Because it's all nice to have theory, but you need to also show that you can solve something. So we solved the following. At the top left, you have an adaptive gift for Helmholtz equations. So I said I wouldn't show it because that would take 20 minutes just to show at least the basics behind that. So that's a Helmholtz equation. And recently we submitted another paper with Chintan on the generalization of that using our estimates. The second thing we did was with Shuang Peng, who is now a professor in China. We did his PhD with us in an ITN network, and he looked at these fracture processes in 2D and in 3D. So you see this crack now is propagating in 3D. And he was one of the first ones to develop isogeometric boundary elements, which has a significant advantage compared to finite elements, which is that you do not need to parameterize the interior of the domain because you only need to discretize the boundary of the domain. And guess what? The NURBS give you already a discretization of the boundary, so you don't need to do anything. You can start directly from the CAD model. I can show you a demonstration because we have a code which is quasi-commercial to do this, which can be used, developed by Hao Jie Lian. And so basically what you do is you start with the NURBS control points, you solve, and you never at any point generate any mesh. So there is no mesh. It all directly comes from the control points. This is a really beautiful application of the idea of isogeometric analysis, because there is no parameterization of the volume, which is one of the difficulties. If you remember, when I showed you this this example, which looked like a T, which was extruded in this direction, right? And then I said, okay, next to these corners here, you may have some problems with the mesh refinement. And so then we split this into several parts. And then we said, okay, we're going to map each one to a cube. And that's going to be easier than trying to map this T to a cube because it doesn't have the right geometry. Similarly with the patch, associated with this hole in the middle. If you remember, we said that each of the 4 patches needed to be mapped to a cube. That was an easier way, because otherwise you would not have the right topology. And then generating a X-like mesh for such a topology here is not at all easy. So boundary elements really go around this, and I think it's one of the very elegant methods that can be used here. Okay, finally, shape optimization for elasticity and acoustics. So there are a few new papers also with a collaborator in China called Lei Lei and Haojie Lian, who has been working since his PhD also in the same ITN, well, at least partly for a very long time. In our group, then came for a postdoc here in Luxembourg and is now in the UK. And so he worked on the problem of optimizing the sound hardness of submarines such that you can minimize their visibility through sonar. So what you see here is the red areas are sound hard and the blue areas are sound soft, meaning that they absorb more and the sound hard material is going to reflect more. And depending on the incident wave, its direction and its frequency, and how it hits the submarine, you would like to have different sound hardnesses. So that's the idea, how to optimize that on the surface. So if you're interested in that, Haojie Lian also did fluid structure interaction using IGA with optimization with Ole Zygmunt in DTU in Denmark. And I think this is excellent work. So if you're interested in fluid structure interaction, as I know some of you are, you can contact him directly. If you do not know who he is, give me a call or send me an email and I'll put you in touch. Okay, that I will skip. I will show you this because it's super elegant and then I'll stop. This is about structural optimization with isogeometric boundary element. So the idea of structural optimization is that normally you start from a CAD model, which is here. Normally, if everything is done using finite elements, you do a mesh generation, you do a structural analysis, then you do a shape sensitivity analysis, which means how sensitive is the thing you're interested in. Let's say the stresses, the weight, the stiffness, how that is sensitive to the parameters, meaning the shape. Then you optimize for a new model. And if you have reached the solution, then you go. If you haven't, then you go back and you regenerate a mesh for the new thing, and you go in circles like this until either you are done, which means you get here, or you continue. And once you have a solution, you need to recover a CAD model because what you have is a mesh. You don't have a CAD model, which means you need to recover the CAD model. So here, in our case, with isogeometric boundary element structural optimization tool, you can directly from the CAD model skip all that mess of mesh generation that goes out the drain. The CAD model recovery goes out the drain also, and you directly optimize for the shape of the object without any need for mesh generation. And we did that on relatively complex objects like that hammer. The hammer's shape was actually obtained by optimizing the shape. We started with a T and we ended up with this, which I thought was pretty amazing. When Haojie showed that to me, I couldn't believe my eyes. And this thing here is a sort of fancy chair where the idea is to minimize the weight and its deformation at the same time, so with certain constraints. And it's quite a difficult thing to do. And yeah, and that was done without any mesh generation of any kind, and it's really beautiful and elegant, I think. That works for acoustics. This is a vase model where we send an impeding wave onto that thing. This is Helmholtz equation. The papers are on the screen if you want to take a picture of it, and you can read that at your leisure. But basically, you can compute the sound pressure on the vase, and that gives you some really nice results. Those are the submarine results that I was mentioning before. The papers are also on the screen, and then I will yes, so you can basically do a lot with isogeometric analysis, in particular with geometry-independent field approximations. And if you're interested in code, you can take a look at two things. One is the code which is generated by my friend in Weimar, Professor Timon Rapsuk, and one of his collaborators, Cosmin Anitescu. The link is on the screen. You can take that down and go there. On our website, University of Luxembourg Legato team, we have a software page where you can take a look at our various codes, which are both in Phoenix, in MATLAB, in Python, and in various other coding languages as well. And with that, I will stop this course, and I will really sincerely thank you for your attention, for the time that you spent listening to me teaching this. I hope that you got something out of it, and it was both sufficiently rigorous and technical, and also informative, and gave you a global view of the field. In 12 hours, there is so much that one can do. If in any case you have any questions on any part of the course, any slide, anything, which, by the way, the slides I will make available to you so that you can read that at your leisure and take your time and go through that again. The handwritten notes will be also made available if it has not been done yet. And we are here to help as much as possible. So we have a team here which is very dynamic and with people that are super open to collaborations. And this is the whole essence of the Driven project, to link up people from the different partners. So I would be really very keen, not only happy, but very, very happy and delighted if I receive messages after that, so that I can put people in touch and let yourself get together and work towards projects that will lead to advances for the community, both at the software level, at the personal level, and obviously at the theoretical and computational levels. So with that, I will stop talking. I will hand the floor back to Katerine so that she can maybe say a few closing words and maybe explain what is going to go next. And there are opportunities for visits, obviously, with the Driven project. This is the whole point. So if you are interested in visiting either us, or if you are one of the partners wanting to visit the other partners, let me and Katerine know, and we're going to make that possible. Thank you so much.
Thank you, Stéphane. Thank you very much for your time, for preparing these interesting sessions for the past 3 days. For the participants, I will send a goodbye thank you email later today with the slides that Stéphane mentioned to you, and also with the links for the recorded videos that you can access it via YouTube, the Legato Team YouTube channel. And please send us your feedback via email about the past 3 days with the course, so we can improve for the next ones. And any questions, please don't hesitate to contact me or Stéphane. And thank you to Arnaud for the support in streaming these 3 days via YouTube.
Thank you so much, Katerine and Arnaud as well.
Okay, so I think we can close the course and wish you all the best. And yeah, hopefully we see each other again
Thank you very much.
in another course by Stefan.
Or by someone else, who knows?
Yes, that too, of course.
Just kidding. So, okay.